Okay, let's continue the ML session. And the first contribution is from iHabs. Yes, just start.
Yeah, thank you everyone. Okay, I'm gonna start to my presentations about the systematic deep learning improved denoising solutions for the synchrone X-ray diffraction and scattering images. And this is me. And if you have any questions, you can connect with these emails. And here we just are gonna to introduce with these questions to show my motivations why I use AI to do the denoising things. First is the data quality concerns and acquisition efficiencies need improvement, saving build time, does damage concerns, and the lack of high quality reference data. So that's the reason why we first use a supervisor way, and the second we use a self-supervisor way to do the denoising things. And now there's two parts. The first part is supervising, and the second part is self-supervised. And for the first one, that we just need some high SNR data as the reference, and we just training a neural network to do this mapping things. But for the second one, we only need the low SNR data, and with some physical priors, we can let the AI to denoising the data only relies on the low SNR data. And here is the things. And the first is just like this is a source pattern that we get from the Morse radius, and with exposure time, this is 0.3 second, and this is 0.1 second, and you can see the contrast. They're in the same contrast, and you can see from this diffraction rings, this is so weak, but this is so strong. So we want to train a neural network first, just do the things, is like find the relationships between them and just map these things to these things. So we can just, because this is just images from the detectors, we can just think this is some kind of nature images, and we just input these images to the neural network, and now we do not get a good result because of the diffraction, because of the scattering patterns. Its intensity is almost like 10,000 or even more. But for the diffraction ring, we care about is only 1,000 or even just 100. Their intensity is quite different. So we just think about why not to use some square root or even to do the log to the data, but we found it's not performance aware, so we just did a very straight way. Just use a mask, put all these pixels to the zeros, and these pixels and these images is still too large for the neural network. So we just cut it directly. That's the reason why you can say the success data I use for the training is this strange one. But it can be used for the data analyzing, and we can still get the same physical information from this customized data or from the raw data. And now we design a neural network, just a UNet neural network. Down simple, up simple is a very simple way, but it have very good performance because of we need to concern about what is suitable indicators. Because in the AI denoising, we have many indicators just like RMSE, ISS, IAM, and PSNR, just like these indicators. But they are just calculating some things from the whole pictures. We don't think that is something we need, because what we need is the physical information behind the physical pictures. So we just do the ICAV integrations from these rings and get some physical information. This is two physical information, it's two Gaussian peaks, and we just do some analyzing based on this information. And now we just calculated. So I decided to calculate, to use these things as indicators to evaluate our module's performance. Because here is just a heat map. There is the relationships between the PSNR, SSM, RMSE. They have high relationships, but for our data, it still have some relationships, but they are not very high. So our physical information is very special. Now I just use this data. You can just look at these three data. But for your eyes, there is obviously not quite big differences. But after the data analyzing, we can say that if we use a very strict way to do the data analyzing, and we can say the one Gaussian peak is just this, and there's another Gaussian peak is just lost. We just extend the exposure time, and now the lost Gaussian peaks is just appear. So we just train a neural network, and the neural network have never seen these pictures. But during the denoising process, you can say that the lost Gaussian peak is just recovered. So that's the reason why we think the neural network is will work well on our domain. And we also do these things in the wax data. And for you, there's a line profiler since here, and you can say the signals with many noises just extend the exposure time, and now you can say the signal is more obviously and the noise is lower. But after denoising, you can say the signal is very clear. And this is just some iterations of these regions, and you can say the performance is also very well. And now we just think about one thing that we can't get the ground truth. We named ground truth just like there is only signals without any noise, but it's hard for us to get from the physical world or our physical experiment. So that's the reason why we want to design some algorithm, just use the physical priors and some AI algorithm and do the denoising things. And you can say that there is four different data, and they all share the same things, that is the symmetry. So for the symmetry, so why the symmetry is so matters, but even you can say the symmetry is not so well in this place or in this place. And just imagine that you have some tools to test the temperatures inside this room. But this things not works where in our middle school, we all have been taught that test it many times and get the mean. The mean maybe is the truly temperatures of this room. So just look at the loss, the way we train the neural network is just use the loss to train it, and its gradient is just like this. And you can say the gradient here is just like this is a mean of your prediction, and this is a mean of your ground truth. And now we can look at these pictures, just like here is the ground truth, is all signal here without any noise. But what we can get is some signals here with high noises. And what we can, and in the last chapters, we just use these pictures as the ground truth because the noise is just smaller. We use this way to prove that the neural networks works, and but from the gradient view, and you can say the noisy one can be separated into these two parts, and the first one is the truth, the mean of the truth, and the mean of the noisy, and we just plus this. And for the ground truth, and you can say there is only one part of the ground truth. If the noisy part is the simples from the Gaussian distributions, if we just plus this signals, we can know the mean is zeros. So if these pictures have Gaussian distribution, is polluted by the Gaussian distributions, from the gradient view, these pictures is the same with these pictures because their gradient is the same. And now, so symmetry and the noisy to noisy algorithm. And now you can say that from this row patterns, it's just a pattern from the bamboo. And now we just mask the unimportant things because noisy-to-noisy algorithm require that just like the ground truth is the same, but the noise is different. You can say if this is a beam stop and this is not a symmetry beam stop here, so this is some information that is different in this line. So that's the reason why we use a mask here. And now we just cut this to the left one and the right one. And now the left one do the symmetrical flip here. And then now we use a common mask to mask it again. And now you can get these two pictures. These two pictures looks like quite same. And now we use these two pictures to train a neural network. Use a noisy-to-noisy algorithm. And now we use these two pictures to just we use these neural networks to predict what is the pictures without noising. And now predict the left one, predict the right one, and combine them to the denoising pattern. And it sounds like it's not a difficult thing for us to do in the algorithm, but you can say that the result here is very impressive. Just like there is a 0.6 second exposure time, this is a Sachs pattern with 0.6 second exposure time, and each images you can see here, there is an ion chamber, and it just shows the shape of the samples, and you can say each pixels inside these pictures is just some physical information extracted from this Sachs pattern, and you can say that there is a lot of pixels is lost because this range is not that strong enough. So if we just extend 1 second exposure time, you can say the pixel here is just appear some here. But if we use the SMAE algorithm I just mentioned, we only use 0.6 second data to do the denoising things, and you can say it seems that all the valuable pixels is just appear here, and now we have another images for you to show some things. Just look at these images. This is just the orientation of the muscles in the mouse radius, and now this is pictures. Just let me show you that for the blue regions, this is the valuable physical information extracted from the 0.6 second exposure time, and we just extend 1 second exposure time, and now you can see this gray region is just growth. And with our algorithm and this gray region, and even though with the orange regions, it's all growth. And now we tested this in another points, and you can see the raw data, and we cannot even to get any information. But for our algorithm, we can get many useful information here. And we also do these things in the wax data, and you can see that we do the things from this 002 peaks and the 100 peaks, and you can see that the 002 peaks SNR is very high, and these three pictures show no differences, even from the numerical views, and its difference is very small. But you can see from here, the raw data is just like this. This is high SNR data, and this is the data what we recovered from the low SNR data, and you can see the effect is very impressive. And now we just do another thing in a time-resolved PDF experiment. We just load the force on the metal glass ribbons and just damage it. And from the machine, we can see the strain and we can see the force. And now from the PDF view, we can also do the data analysis and just get this thing. And you can see the red one. This red one is the raw data analyzing is the data analyzing result from the raw data. And you can see this blue one is the data analyzing result from the denoising one. And for the raw data, you cannot to plot these lines because you cannot even to decide which positions is this is this peaks. So after denoising, you can say this peaks is just changed smoothly, and now you can plot string lines that change with times, and it's almost the same with the same with the result that we get from the machine. So here's the 3 different experiments to show that the SMAE algorithm is work. And if anyone you interested in this, if your data have its symmetry inside, you can just use this algorithm to denoising your data. And finally, this is just a summary, and just like for the supervisor one, we rely on high SNR data. Just means we need to get some data with a longer exposure time. But for the SMAE algorithm, we not rely on the high SNR data. We only rely on your symmetry. If your data have symmetry, we can do the denoising things itself, and it can get a result even better than extend your exposure time. That's all.
Thank you very much. For questions, we do it afterwards. We have to really move on to the next talk already.
Thank you.
Sorry.